Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for the week number 4 of our course of communication systems. In our previous lecture, we talked about different modulation schemes, and now we will be starting a detailed mathematical analysis of each of the modulation scheme that we have briefly discussed before. So let us begin our discussion with the amplitude modulation. We know that in amplitude modulation, the information signal varies the amplitude of the carrier sinusoidal wave. That means the information is placed in the amplitude of the carrier wave. So instantaneous value of the carrier amplitude changes in accordance with the amplitude variation of the modulating signal. So in other words, the information of the information contents of the message signal, they are placed in the envelope of the modulated carrier. So that is generally represented by an imaginary line, because there is no physical waveform at that place, but we in order to show those variations, we generally draw an imaginary line. So this is the graphical illustration of the message signal as well as the carrier wave. The first part, this shows a unmodulated carrier wave. Here you can see that it's a simple sinusoid. But once we do the modulation, that means we perform the amplitude modulation, so this amplitude would be changing with respect to changes in the amplitude of the sinusoidal modulating wave. So let us assume this is our modulating wave. So we have, for simplicity, we have taken this as a sinusoidal modulating wave. So we can see that as the amplitude of modulating wave gets increased, the amplitude of the carrier wave is also increasing, and when the amplitude of carrier wave starts to decrease, the amplitude of this modulated carrier wave also decreases. So this variation actually these variations, they are following the modulating signal. So in other words, this envelope with this dotted line which is shown here, this envelope represents the variations that we observe in the modulating wave. So this is the illustration how the amplitude modulation represents the amplitude modulated waveform represents the information contained in the message signal. So what is the mathematical form, or how can we represent the mathematical way of representing that modulated signal? So let us start discussing that mathematical description. So first we assume a carrier wave. So I have assumed that carrier wave to be equal to AC cos omega ct plus phi. You can notice that I have ignored the phase angle in this modulated in this carrier wave, because we are interested in amplitude modulation. Phase for this particular stage is not important, so we are just ignoring the phase angle in order to provide some simple expressions. You must notice that if there is a phase, it will not change the expressions as well, because we will be dealing with the amplitude only, not the phase angle. Okay, so if we have a carrier wave and we have a message signal which is represented by xt, so what is the AM signal or amplitude modulated signal? So it is a combination of this carrier and the message signal, which is mathematically represented by this expression AC 1 plus mu xt plus into multiplied by cos omega ct. You can notice that this AC and cos omega ct, these are actually this represents the carrier wave, and this part is related to the message which contains xt. For simplicity, we can break this expression into two terms. First one is the carrier wave AC cos omega ct, and second term represents the variations that we observe because of the variation in the message signal. You can see that this is AC mu xt cos omega ct. So this, whenever this xt varies, so this overall amplitude would be varying. So one important thing that you should notice is that the mathematical operation that describes the amplitude modulation is multiplication, because this carrier wave and the message signal, they are being multiplied in time domain. You can simply see that xt and cos omega ct, they are basically multiplied. So the mathematical description of am is actually that of multiplication. The mathematical operation of multiplication would provide this amplitude modulated signal. This constant number mu here, this is mu, is which we have introduced, is actually a constant number which is named as modulation index. If you recall, in our last lecture I was trying to explain that in amplitude modulation the variation in amplitude should be in proportional to the variation in the message signal. So you can treat this mu as a proportionality constant. So this is that proportionality constant which relates how much variation will be there when there is some variation in the message signal. So this will relate the variation of the message signal to the variation in the modulated signal. So this is named as modulation index. Sometimes we call it modulating factor, sometimes we call it modulation coefficient, sometimes we call it degree of modulation. So there are different terms that are being used to describe the same quantity, which is mu. Practically, this modulation index mu is defined as the ratio of amplitude of the message signal to the amplitude of the carrier wave. So if we divide the amplitude of message signal, or maximum possible amplitude of the message signal, to the amplitude of the carrier wave, so we get the modulation index. Most commonly we try to represent this modulation index in percent modulation, in percentage value. So simply we multiply this mu by 100 and gets a percentage value of this modulation index. So if you closely look at this expression again, you would see that this cos omega ct is actually a sinusoidal function which is representative of the carrier wave, and this entire part, this is actually the amplitude of this sinusoidal function. So this is actually time varying amplitude, as we should observe from this diagram, this waveform of the amplitude modulated signal. You can see that the amplitude is varying with respect to time. So this time varying amplitude, or this envelope, is being represented by this mathematical expression AC1 plus mu xt. So the signal's envelope is actually time dependent, which is given by this value here, at is, which is given as AC1 plus mu xt. Okay, in order to illustrate what is the effect of this modulation index mu onto the waveform of the modulated signal, so let us draw two different waveforms corresponding to two different values of mu. So for first case I have plotted the waveform which is for mu less than 1, and for second case I have plotted a waveform for which mu is greater than 1. So assuming this is our message signal, so it's a randomly selected some waveform. So once we do the amplitude modulation, in that case the amplitude of carrier wave will be varying in accordance with the message signal. So you can see that this envelope is following this message signal, is presented in part A of this figure. For this particular case, you can see that the envelope directly shows the message signal. So from the envelope we can perceive what will be the message signal in this particular case. But what if we have mu greater than 1? Having mu greater than 1 means we are working in the case where proportionality constant is high and there is a large variation in the amplitude whenever it is applied to in an amplitude modulation scheme. So you can see that we have plotted this waveform again, this amplitude modulated waveform, but this time the variation is going with to a higher value because of this high value of mu, which is greater than 1. The problem occurs when this goes towards this negative side. So as soon as it starts to go downward here, at this point it will cross this zero amplitude axis. Crossing zero amplitude axis means there will be a phase reversal. We have previously discussed that a negative amplitude does not have any meaning. Rather, having a negative amplitude means we have 180-degree phase shift here. So that means once this waveform crosses this zero line, so there will be a phase reversal, and after phase reversal the amplitude modulation would be the envelope would be reverted back with a different phase. So it will not be possible to extract the information from this envelope detection. You can see that this envelope would look somewhat like this, which is actually different than the original envelope. So having mu greater than 1 gives us a problem of phase reversal here, which makes it harder to demodulate the signal, and eventually we experience an envelope distortion in the signal. This condition is generally named as over-modulation condition. So for most cases, amplitude modulated signal, we generally do not want to have this over-modulation condition. So we try to keep this mu less than 1. So we have to keep this mu less than or equal to 1 to ensure that this envelope does not go negative, or we do not encounter this phase reversal condition, or we do not encounter the distortion that is appearing because of the phase reversal because of this over modulation. So most commonly applied AM modulation schemes, they typically use this mu to be less than 1, which is the case of under modulation, which is this condition sometimes named as under modulation. You can see that the maximum amplitude that a modulated wave would take can be given as A max to be equal to AC 1 plus mu, and the minimum value that it takes, that will become equal to A minimum is equal to AC 1 minus mu. So these are two extreme values or extreme amplitudes that will be present when we do amplitude modulation. However, most optimum case would be the one when we keep this mu to be equal to exactly equal to 1, or that means if we have 100% modulation. So with 100% modulation, you would see that the envelope, the maximum value of envelope would reach double of this carrier amplitude, and the minimum value would reach the zero amplitude, but there will be no phase reversal. So practically the modulation index should be kept between 0 and 1. So most of the practical cases, they are designed to have this property. We typically keep mu slightly less than 1. Of course, we cannot allow mu to be greater than 1, as we have previously discussed that it causes distortion in the signal, and this distortion, sometimes if distortion is high, in that case we will not be able to detect the signal. For voice and video, if there is a distortion, in that case for voice transmission it produces some unwanted effects in the sound coming out of the speaker. Similarly, for distortion in the video signals produces a scrambled or inaccurate picture in the TV screens. One more thing that I want to represent is that we can calculate the modulation index by observing the waveform, AM waveform in the oscilloscope. Simply we need to identify the maximum attained voltage and minimum attained voltage. So by calculating the maximum and minimum values of these amplitudes or voltages, we can easily calculate this modulation index, which is given by this formula a max minus a minimum upon a max plus a minimum. You can easily derive this formula by using the two relationships which are given here. You can simply uh, manipulate these two relationships to separate out the values of mu, and you would see that the mu would become equal to this expression a max minus a min upon a max plus a minimum. So if we have a waveform available, from that waveform we can easily calculate modulation index as well. Okay, so how the AM signal is generated and the mathematical form that has been discussed so far. So in order to conclude our discussion, let us take a simple problem. So we have an audio wave which is actually message signal, representing message signal 15 sine 2 pi 1500 t. We have a carrier wave which is 60 sine 2 pi 100,000 t. So we want to sketch audio signal, we want to sketch the carrier wave, we want to construct the modulated wave, we want to calculate the modulation factor or percentage of modulation. Also we want to identify the frequencies which are available in this system in part E and F. So let us start by identifying different quantities that are present in that are available to us. So we have two waveforms which is needed for the modulation case. One is the modulating signal, which is message signal 15 sine 2 pi 1500 t, that, and second is this carrier wave which is 60 sine 2 pi 100,000 t. So first two parts are the simple sketching of this audio signal and the carrier wave, and you can notice that these audio signal and carrier wave both are represented as sinusoidal function in that sine function. So we can simply plot the sine function with appropriate frequencies. So this is modulating signal, the audio signal with the amplitude of 15 volt. You can see that the amplitude is given as 15, whereas the carrier is a high frequency sinusoid. So you can see that it has a relatively high frequency with an amplitude of 60 volts. So we have a carrier wave which is again represented by a sinusoidal function. Now second thing is to sketch the modulated wave. We know that the modulated wave is actually the carrier wave whose amplitude varies in accordance with the message signal. So we have this this carrier wave here. You can see that this is representing the modulating signal. This is the this horizontal line is representing the amplitude of this carrier wave. This amplitude actually serves as the base line for this modulated signal. So if we superimpose this message signal onto this carrier wave, it would look somewhat like this, and you would see that the overall message signal or modulated signal would follow this type of pattern. So the amplitude that it will take will be starting from 60, and because the message signal has additional 15 volts of amplitude, so the maximum amplitude that it will take will be 60 plus 15, which is 75. So if I plot this waveform, it would look somewhat like this. You can see that this dotted line here is actually representing the level of the carrier wave, and on top of the carrier wave we have superimposed the message signal, which is a sinusoidal function of amplitude 15. So you can see that from point of the reference of the carrier wave, the amplitude is increasing by 15 units and decreasing by 15 units, which goes up to 45 units. And same thing appears in this negative side as well. You can see that the same variations are observable at the negative side. So this waveform is representing the modulated waveform which is present, which will result when we modulate this carrier wave by using the given sinusoidal message signal. The fourth part is to calculate the modulation factor and the percentage modulation, modulation index and percentage modulation. We know that modulation index is actually defined as the ratio of the amplitudes of this message signal and the module and the carrier wave. So if we divide the amplitude of the audio wave with the carrier amplitude of carrier wave, we would see that the modulation index comes out to be 0.25, and we can simply convert this modulation factor into percentage modulation by multiplying it by 100. So we see that this particular waveform has 25% modulation. E part is to find the frequencies in the audio signal and the carrier wave. We can easily identify those frequencies. The audio signal has the frequency of 1500 Hz. You can see it from here, because this entire expression gives omega. So we have 2 pi into 1500 Hz, that means 1500 Hz. So the audio signal has a frequency of 1500 Hz, whereas the carrier wave has a frequency of 100,000 Hz. So we can simply calculate, we can simply identify the frequencies which are present in the audio signal and the carrier wave, which comes out to be 1500 and 100,000 Hz. The last part is important. You can see that we want to identify the frequencies that would show up in the spectrum analysis of the modulated wave. So what frequencies do you expect when you have done the modulation? You can see that this E part was referring to the frequencies which are before modulation, that is frequencies in the audio signal and the carrier waves. But now we are interested in identifying the frequencies which would be present in the modulated wave. So in order to identify those frequencies, let us quickly recall that the mathematical form of the AM signal. You can see that the mathematical form of AM signal is actually has two parts. One is the carrier itself, and second is the product of the message signal and the carrier. So you can see that there is a product of xt and omega c, or cos omega ct. So from first part we can conclude that the carrier frequency would be there in the output side, because we have a definite term related to the carrier. So the output of modulated waveform contains one frequency, which is the carrier frequency. Of course, that will be there. What about this product xt and omega ct? If you look at this product, so it will give rise to two frequencies. How there are two frequencies? Let us take our problem, because we are working for two signals. One is the audio signal, which has this form of sin 2 pi f/at, and we are working the other signal is the carrier wave, which has the form of sin 2 pi f/ct. So if we multiply these two, so you would see that sin 2 pi f/ct and sin 2 pi f/at, You can see that this is a simple product to sum formula that we use in trigonometry. So if we apply that trigonometric formula, you can see that we get two terms. One is the cos 2 pi fct minus 2 pi fat, and second is the cos 2 pi fct plus 2 pi fat. You can see that in first term both frequencies, they are actually subtracted, fc minus fa, and in second term both frequencies, they are added. So concluding, what I want to say is that if we get the product of these two terms, that is message signal and carrier signal, it will give rise to two terms, one in which the frequencies are added and other term which in which the frequencies are subtracted. So the modulated waveform would have two other frequencies. One would be fc plus fa and another would be fc minus fa. So the output spectrum, the modulated wave spectrum, would contain three frequencies. One is the carrier frequency, second is the sum of carrier and audio frequency, and third is the difference of carrier and the audio frequency. And we know these frequencies, so we can easily calculate the numerical values for each of these. So carrier frequency is 100,000 Hertz, as we have already calculated. The sum of two frequencies will be 100,000 plus 1500, which gives you 100,000 and 1500 Hertz, and the difference of these two frequencies will give you 98,500 Hertz. So the output modulated waveform, that will contain the these three frequencies, which are 100,000 Hertz, 100,000 and 1500 Hertz and 98,500 Hertz. So you can see that in this problem I tried to show many different things. First, how we can construct the modulated waveform, which we have done it here by superimposing the message signal onto the carrier wave and following the variations appearing in that superimposition. And second, how we can calculate the modulating factor by dividing the amplitudes of both the terms. And third important thing, we have discussed the frequency contents available in the modulated wave, and we see that the modulated wave contains three different frequency contents: the carrier plus the message signal, and carrier minus the message signal frequencies. So these are the frequency contents that will be present in the modulated waveform. So let us take another problem. So I want to find modulation index and percentage modulation of AM signal, which is shown here. You can take it that if you are getting an AM signal, you have simply applied it onto an oscilloscope and you have got this type of waveform here. In order to calculate the modulation index from the waveform, what we need to observe is the maximum attained amplitude and the minimum attained amplitude of this waveform. So you can see that from here we see that the maximum value of the amplitude A max is 50, whereas the minimum attained value A minimum is 15. So the modulation index can be calculated by this simple relationship: A max minus A minimum upon A max plus A minimum. If you substitute this value, so you get the value of 0.538, or in other words, this waveform, AM modulated waveform, represents a modulation index or percentage modulation index of 53.8%. Now let us move on to the frequency domain description of AM signal. This is the first line. This is the time domain representation that we have discussed so far. So you can see that if we take a Fourier transform of this signal, I'm only representing the transform for f greater than 0, that is for positive side of the spectrum. So because we know that the negative side of the spectrum is exact replica of the signal. So you can see that the cosine function, the transform would be represented as an impulse function here, whereas this mu xt, it will be represented as a transform of xc shifted to the carrier frequency fc. So graphically, if you want to show the transform, this is the transform of the signal xt. You can see that the signal is a band limited with the bandwidth of w. So the spectrum of the signal extends from 0 to w hertz. When we take the modulation, so what happens, the same spectrum is reproduced at the center frequency of the carrier fc. So this becomes the center frequency where you have the carrier here, and the spectrum has the same shape, but its place at a relatively high frequency, which is represented by the carrier frequency. So this spectrum can be viewed in three parts. You would see that the first is the carrier term that we have previously discussed as well. So this carrier is represented as an impulse at the carrier frequency. So this impulse is actually representing the carrier. This part, which is the positive frequency here, is available in the spectrum of the modulated signal as the upper sideband, whereas the negative part is also available at the positive frequencies in the amplitude spectrum, which we call a lower sideband. So actually this entire spectrum is shifted at the relatively higher frequency, which centered at the carrier frequency, and you can see that the spectrum has the same shape at the frequencies above the carrier frequency and the frequencies which are lower than the carrier frequency. Typically we name them as side bands, and you can see that these two side bands, they are actually replicas of each other. They are symmetrical about this carrier frequency. So you can see the spectrum is now divided in three parts: carrier, the upper sideband, and the lower sideband. So these sidebands, they occur whenever we do the modulation process in the frequency spectrum. So these sidebands, they generally occur at above and below frequency. Previously we have talked about a simple sinusoidal wave, and we saw that it generated two sideband, one at the frequency of fc plus fa and second at a frequency of fc minus fa. But whenever we are working at the complex signals, complex wave, voice or video signals, so typically those signals, they occupy a range of frequencies. In that case, the spectrum extends at the range of frequencies. So upper sideband would be available up to fc plus w, and the lower sideband will be available until fc minus w, where w is the bandwidth of the message signal. As illustrated here, the upper sideband ends at fc plus w and lower sideband ends at fc minus w. Because we have two sidebands, so there is another term which is used for amplitude modulation, which is named as double sideband. So this is a double sideband with carrier, because we have carrier as well. Another important parameter related to the modulation is the bandwidth. We have previously discussed that bandwidth is one of the important parameter which we need to account whenever we are talking about a transmission. So bandwidth of the carrier signal, this modulated signal, is actually starting from this end of the lower sideband and will end at this end of the upper sideband. So this band is the bandwidth of the modulated signal. So if we want to calculate the bandwidth, so it will be whatever the frequency of the upper sideband we have and minus whatever the minimum value of the lower sideband we have. And if we substitute, if we subtract these two, we will see that this bandwidth comes out to be 2W. So this entire bandwidth is 2W. Compare this with the unmodulated signal. The unmodulated signal had the bandwidth until W. So this was the bandwidth of the unmodulated signal, but the modulated signal requires a bandwidth which is 2W. That means after modulation our bandwidth requirement become double. So AM requires twice bandwidth needed for transmission than the baseband signal without modulation. So this is one of the important characteristics of AM signal, that it requires twice the bandwidth of the unmodulated signal. So let us take a very simple problem. A standard AM broadcast station is allowed to transmit modulating frequencies up to 5 kHz. So modulated signal has the maximum frequency contents up to 5 kHz. If the AM station is transmitting on a frequency of 980 kHz, that means the carrier that is incorporated in that AM transmission has the frequency of 980 kHz. What are the sideband frequencies and the total bandwidth? So we know that the sideband frequencies, they are actually represented by sum and difference of the carrier and the message signal. So upper sideband frequency would be FC plus W, which turns out to be 980 plus 5, that is 985 kilohertz. Whereas the lower sideband frequency will be FC minus W, which is 980 minus 5, which is 975 kilohertz. So the available bandwidth will be the difference of this upper sideband frequency and lower sideband frequency. You can simplify it to get 10 kilohertz value. Alternatively, we know that the bandwidth is actually double of the bandwidth of the message signal, which is 5 kilohertz. So if we simply double it, so we will get the same answer, that is 10 kilohertz. So concluding the discussion related to frequency domain signal, we see that whenever AM signal is represented in frequency domain, so basically it appears as three parts. One is the carrier part, second is the upper sideband part, and third is the lower sideband part. And lower sideband and upper sideband, they are symmetrical. So they are symmetrical about the carrier. Third important thing is that the AM signal requires double the bandwidth as compared to the unmodulated baseband signal. So we stop this lecture here. In our next lecture, we'll talk about another important parameter, which is the power consumption or power requirement of the AM broadcast. So we'll be talking about power in our next lecture. So we stop at this stage. Thank you all.